So welcome everyone to this very exciting occasion. My name is Jeff Miller. I am head of public affairs at the lab. Our brief presentation program this morning will begin with remarks from Don DiPaolo, who is our associate lab director, followed by remarks by UC Berkeley Chancellor Robert Birgeneau, followed by an introduction of Saul by Bob Kahn, who is our current head of the cosmology group. Saul will then speak for a few minutes, and then that will be followed by media questions, which I will moderate from here. I'd like to acknowledge a few people in the audience with us today. The acting physics division director at the lab, Dave Nygren, right here. Please stand. Francis Hellman, chair of the Department of Physics at UCB. Mark Richards, Dean of Mathematical and Physical Sciences at UC Berkeley. And Harriet Kung, Basic Energy Sciences, Department of Energy. So with that, I will now leave the podium, and please welcome Don DiPaolo, Associate Lab Director.
Thank you, Jeff. This is a real pleasure. On behalf of Berkeley Lab Director Paul Alivisatos, who is traveling in Norway at the moment, and I'm certain is very disappointed not to be here to share the excitement, I, as a representative of the entire Berkeley Lab community, want to congratulate Saul on being awarded the Nobel Prize in Physics, the lab's 13th Nobel Prize in its 80-year history. We also congratulate Saul's co-recipients, Adam Riess and Brian Schmidt. In discovering that the expansion of the universe is accelerating, the exact opposite of what was expected, Saul and his co-recipients fundamentally changed our view of the origin and fate of the universe. They also introduced us to the concept of dark energy, that mysterious something that is fueling this acceleration. Science sometimes inches forward. This was one of those moments when it leaped across galaxies. And while Saul is literally the star of the show today, we hope, and we say this on behalf of America's national laboratories, that this award sparks the imagination of young would-be scientists everywhere, those who look into the night sky and wonder about what they see. Saul wondered and brought us all a great gift. Thank you, Saul, for sharing that gift with the world, and congratulations again from your many admirers and friends here at Berkeley Lab. I would now like to introduce my colleague and friend, Robert Birgeneau, Chancellor of UC Berkeley.
So what a great moment. So good morning, and thanks all of you for coming to celebrate this morning's announcement of the 2011 Nobel Prize in Physics. This is the 22nd Nobel Prize won by a Berkeley faculty member, the majority of which, 13, have been won by faculty who were jointly appointed at the laboratory and at the university, like myself, actually, except without the Nobel Prize. In fact, I became a chancellor as a consolation prize, but that's so let me begin by offering our heartiest congratulations to Saul. So as you just heard, Saul's sharing the prize with Adam Riess of Johns Hopkins University and Brian Schmidt of Australia National University. Saul led the Supernova Cosmology Project. You'll hear some more about that. That discovered the accelerating expansion of the universe at the same time as Riess and Schmidt worked on the problem through the competing high-Z supernova research team. But remarkably, Riess wasn't in Australia when he was working on the competing team. Actually, he was here at Berkeley as a Miller Fellow working with Alex Filipenko. So it's pretty interesting sociology. It happens that this weekend I was in Cambridge, Massachusetts at the American Academy. They were inducting new members. There were a number of Berkeley people being inducted. And at the table, which had mostly humanists, the dinner table, they started grilling me about who I thought should win the Nobel Prize in Physics. And I gave a speech on Saul's behalf about the sort of profound importance of his work and how fully deserving he was and what a great person he was. And actually, it's my notes, so I feel really good about 2 days in advance having gotten it correct. So, one really important point to make, and it's not just because Harriet is here, but I think for the group is, universities like Berkeley and national laboratories like Lawrence Berkeley Lab are really the only places left in North America where this kind of profound work can be done, where we can pursue knowledge for its own sake. And so I can't emphasize, the importance of us maintaining our commitment to being willing to put enormous energy into exploring knowledge at its most fundamental level. And it's not, and it's really our commitment to do that. This work is particularly, all Nobel Prize work is impressive. I particularly like this research because, as Saul himself explained, and probably will explain later today at 1 o'clock, this wasn't a eureka moment which happened in 30 seconds. This represents decades of work. And even the discovery itself, as Saul will describe to you, was something where when they first looked at the data, because it went so much against conventional wisdom, right? They wondered, can this really be true? And they did the kind of really, hard science that is necessary in order to make a great discovery. So this is really admirable work. Work like this doesn't happen in a vacuum. One of the things that's really important is here, both at the laboratory and on the campus, that we have an outstanding set of colleagues, for people like, take the risk of naming a few people, but there was obviously Riess himself as a Miller postdoctoral fellow, George Schmidt's pioneering work before, great work done by Alex Filipenko, who participated in both teams, and then this beautiful confirming experiment by Paul Richards, which came shortly after Saul's work and confirmed that Saul's work was correct. And then also a panoply of outstanding theoretical astrophysicists who were working on the theory of the universe, for that matter. So it's really important. People can't, maybe Saul, you could have done this work in isolation, but most of us, anyway, need this penumbra, and we need to maintain this kind of outstanding set of people, both here at the lab and on the campus. One of the great aspects of Saul is that, of course, he's a great researcher, but all of you know he's also a great teacher. And indeed, his faculty colleagues, the Academic Senate on campus this past year, recognized him as one of 2 distinguished faculty lecturers. And Saul, for those of you who attended that, you'll know Saul just gave a wonderful lecture, and it's a tradition that I host a dinner for the lecturers. That was Saul and Linda Williams. And the evening could have gone on forever when we open it up to questions, both for Linda because of the very beautiful work she does on film and television, and Saul, the origins of the universe. And that dinner was a reminder of the greatness of Berkeley and its breadth. So let me just finish up and say, I and I know all of you feel blessed to be at institutions which have colleagues like Saul who can't be bought by rich private universities.
That's true.
And have shown that we LBL as a great national laboratory in UC Berkeley is the world's finest public institution. Our places we take great pride in. It's our 22nd Nobel Prize, and there will be many more in the future. And let me finish by congratulating Saul. So now it's my pleasure to welcome to the podium Bob Kahn, current head of the cosmology group at Berkeley Lab. You all know him well. And he also happened to be division director for physics during the initial supernova discovery. So he's very tightly tied to this Nobel Prize.
Thank you, Chancellor Birgeneau. It's a great privilege to introduce Saul Perlmutter, winner of the 2011 Nobel Prize in Physics for the discovery of the accelerating expansion of the universe through observations of distant supernovae. The discovery of Saul's team, the Supernova Cosmology Project, and their competitors, the High-Z Supernova Search, revealed that 75% of the energy in the universe is not due to matter, not even to some undiscovered sort of matter. I like to say this is the biggest discovery in the history of science and will remain so forever, since it only leaves 25% for everyone else. This 75% we call dark energy, mostly because we're in the dark as to its nature. But discovering dark energy has enabled us to understand the age of the universe, its past history, and its future. This kind of fundamental discovery was possible here at the Lawrence Berkeley National Laboratory because of the support provided by the Department of Energy. It is built on a legacy of research begun by Louis Alvarez and continued by others, including Rich Muller, Saul's thesis advisor, George Smoot, our Nobel laureate from 2006, and Saul himself. The discovery of dark energy has inspired research around the world, and we at LBNL are busy with ongoing experiments and plans for future ones aimed at exploring this mysterious but ubiquitous constituent of the universe. Saul and his team were undaunted by skeptics who said this couldn't be done. It's thanks to his courage and wisdom that we're here today. Saul?
Well, it's been a rather busy morning, and I'm very glad that I'm sort of home speaking to you guys because for once I haven't had a chance really to prepare much to say, so I'm going to be somewhat more extemporaneous than usual. I will say that it's interesting to wake up at 2:45 in the morning by somebody on the phone saying that they're a reporter and they want to know how you feel, and. And I felt fine, but I didn't know. I said, well, why? Why do you ask? And then, of course, my wife Laura quickly pulled out the iPad and tried to determine whether or not this was a hoax, or where this feel. So it wasn't until an hour later that I finally heard from the Swedish Academy itself. And so meanwhile, was working through a chain of reporters, on call waiting one after another. And eventually proved that really the Swedish Academy did exist, and they were glad I exist, I gather, because they were starting to get nervous about the fact that they were not catching the third of their recipients, and of course they had the sad news the previous day of having missed somebody, so they were wanted to make sure they had. They told me, so I was alive and well. I was asked maybe to say a word or two about what the discovery was itself. That led to this, and so I'll just, in a nutshell, describe what it was for those who haven't heard. This began with a project which several of us here in the room, although I'm looking for Rich and Carl, were working on, and we realized that by studying right back there outside the room, we realized that because we had been developing a technique. That actually was something that Louis Alvarez had recommended, Rich Muller's Nobel laureate advisor, to find supernova using the newly capable automated capabilities that you could do with computers. And with the detectors that are now in the back of every one of these cameras, the CCD detectors that are so ubiquitous these days, we now could actually find supernova in a much more organized way. Carl actually had suggested that we try out the same idea going much further and see whether we could find supernova far enough away that they could act as measuring distance markers across the universe. And we could do an experiment that had been proposed, 50 years earlier by Bada and Zwicky to measure the slowing of the expansion of the universe. And the idea is that back in the 30s, when Hubble saw that the universe apparently is getting bigger all the time, all the distances between galaxies are increasing, it was recognized that you might expect that would be slowing down because all the gravity in the universe, all the stuff in the universe would attract each other, and it would slow the expansion. And so the obvious question was, well, how much is it slowing down, and is it slowing enough? Is there enough stuff in the universe that it could slow down to the point that it would come to a halt someday and perhaps turn around and collapse? In which case, we could discover that the universe was really going to come to an end. And this was, getting towards the end of the century, and we were thinking that this would be a great millennial project to be able to walk around saying the universe is coming to the end and we have the data, or not. as the case may be. And I thought it was exactly the kind of project that any scientist would love, because you're going to ask a potentially very philosophical question, a question about the fate of the universe. And it also turned out to be connected with this little minor question of whether the universe was infinite or not, and in space. And we thought that was a pretty fun question too. And so I couldn't imagine a better project that you could actually ask such a philosophical question by going out and making measurements of the brightnesses of these exploding stars. And each star that exploded, it sent its signal to you. It traveled for 1 billion or 2 billion or 4 billion years to reach us. And it gets fainter on its way. By the time it reaches us, it looks much fainter. And of course, you can tell how far away it is by how faint it is for these particular kinds of supernova, where they're all intrinsically about the same brightness when they peak. So that means that you can say, this supernova here, that light has been traveling for 2 billion years, and that supernova there, it exploded 4 billion years ago. And so if you had this whole series of supernova, you could mark off different points in the history of the universe. Each supernova could also tell you a very important piece of information, which is how much has the universe expanded since the time that the light left that supernova. And that's just because as the universe expands, everything that's not nailed down in that universe expands with it. And that includes the very wavelengths of the photons of light that are traveling to us from the distant supernova. So the light leaves these supernovae, this particular kind of supernova, looking mostly blue. That's a short wavelength. By the time it reaches us, it's been stretched right along with the universe, and it looks red. And the more stretch of the universe since the time of the explosion, the more red that light looks. It's called redshift, as many of you know. And so in the end, all we had to do is take the redshift and the brightness of the supernova, and we were able to plot the stretch of the universe, how much the universe has stretched since each of the different times that one of the supernovas represents. And what we found when we looked at the plots, was, as of course you know, is that we did not see the expected curve of the universe slowing down due to gravity. It clearly wasn't slowing down enough to come to a halt. In fact, it wasn't slowing down at all. It apparently has been speeding up in the whole last half of the universe that we were watching. So this was what we saw. Of course, everybody asks, what was the aha moment? And I always say that it wasn't much of a aha in the conventional sense, because you first plot up the data, just managing to get all your raw data onto the plot, and before you finish doing all your calibrations and tests, and the data's all over here on the wrong side of the plot. And you say, well, okay, we haven't done the calibrations yet. What do you expect? And we then calibrated, and we then worked, and we reworked. And over the course of months and months, we managed to convince ourselves that actually the data didn't need any much further calibration. In fact, whenever we calibrated, the data looked more strongly suggesting that the surprise was what we were seeing. So by the end of 4 months, as a group, we pretty much decided that this is what we were going to have to go with, and we were going to have to tell our scientific community that this is a surprising result. Here's the reason that we believe it, but we think it's true. And so in that sense, I've been saying this is probably the slowest aha moment that you'll hear about. So this is the discovery, and of course now with all the community of scientists here, we've been having the fun ever since, trying to figure out why is this universe doing such a crazy thing? Why is it speeding up? And it could be that, as Bob had mentioned, most of the universe is dominated by a dark energy that pervades all space and is causing this acceleration. It could be, perhaps even more surprising, that Einstein's theory of general relativity needs a little bit of a tweak, perhaps acting slightly differently on these very large scales of the universe. But at this moment, I would say that the question's wide open, and it's really the place where the measurements have to fill in the gaps. The theorists have been working very hard. I think I had a quick look, and we're estimating that there's a paper basically every day since the discovery with some theoretical ideas on the topic. And so there's no lack of theories, but we really need some more guidance from the actual measurements. And so that's really where all the work is going on that we're doing next. So the only other thing I'd written down that I wanted to comment on about is that I think this kind of prize is really a great moment just to step back and think about what it is that we are able to do together as humans when we work together, and that this kind of, this science in particular is a case where many different cultures and civilizations actually have contributed bits of of the concepts that we now use in our understanding of the universe. So it's really a human story going far back. And it also recognized what's possible to do when whole communities of science come together and are able to work together in the way that they did in this project. In particular, there were these two international teams. One of them that was centered here, but had members all over the world. The other team was led from Australia, but also all over the world. And the fact that those two teams together ended up representing a good fraction of the community of supernova scientists when you put them all together, I think really reflects very well the sense in which this kind of result doesn't come about from a lone scientist walking down the lab coat to a laboratory. It's really the work of a whole community of people working together, introducing ideas and concepts that makes this kind of thing possible. And I think people forget that science isn't a lonely activity. It's really maybe the ultimate social group activity that I may know about. Let's see, what else was I going to comment? I was also going to comment that I sort of love the fact that this particular result shows some of the two-headed aspects of discovery like this. On the one hand, it was only possible to discover what we did because of how much, as a science, a field, physics, we've come to understand about the universe. That we used all the pieces that we put together the puzzle in order to interpret what we were seeing in the supernova data, and that allowed us to make this measurement. So it's amazing how much we figured out. But on the two-headed, the other head, it's amazing how big mystery can still be left over and how much we still have left to discover. And so I think one of the real pleasures of doing science, I hope throughout any day in the next few centuries, is this idea that you're going to be able to build on so much that we figured out, and yet there's so much more for us to discover. And so I think it's one of the real pleasures of this kind of result, that you get to sort of see it writ large, very large in this case. Let's see, what was I going to comment also? And I was going to comment that in some sense, these two aspects of science remind us that really science is a method, not a finished product, and that we don't know where it will lead or what new magic it will give us the power to do in the future. So we've no idea whether or not we'll end up being able to use this particular bit of knowledge about the world to do something magical with the world around us. But we do know that in the past, whenever we've made a major step forward in our understanding of how the world works, we've often been able to do more with our world and solve more problems. And so that's I think the only way that we can proceed as basic scientists, is to try to see what we can understand and hope that opens up more possibilities for what we can do in the world. And then because of these two aspects of fundamental science, I think in some ways it's both sort of an inspiring art form and then a hard-nosed practical investment. And so the occasion of a prize like this is an opportunity, I think, to thank and honor sort of those gurus of the art form and maybe the shrewd practical investors who both contributed to this result. And so I wanted to just quickly go through a few of them. First, of course, there's the fact that everybody comes from their intellectual tradition of where they grew up and who they learned from. And I learned huge amounts about how to approach the world as a scientist from my thesis advisor, Rich Muller, who I don't know if he's here, who is a scientist here at the lab and also at the university. And of course, that carried on a tradition here at the lab that had been built up for many years of innovative ideas for science, but also real rigor in how you examine things. And so the fact that this grew out of Rich Muller's group, it was no accident at all. And the fact that it was the kind of project that starts with bouncing ideas around between group members, and Carl Pennypacker, who I just saw before back, was so instrumental in getting this thing going off the ground. Having a scientist who was absolutely undaunted and optimistic that we could do anything, sitting next to me, is I think why we got this whole thing started in the first place. Then the fact that the project is purely teamwork. I mean that you're working so closely with all the teammates around, and Many of them are all over the world now, but there are a number here in the audience today. So maybe I should ask Greg and Alex, Greg Goldring, Alex Kim, and I don't know if Peter Nugent's here. Maybe if you stand up just for a quick second. Just representing... Peter, thank you. And they're representing the fact that, that we were all just working, round the clock with each other, and we were on the phone all the time and trying to make the things work. And that's the only reason I think that results like this come about, because of this team, this capability that you can do as a team. I think the fact that Bob Kahn introduced me today is no accident, because he also provided the environment as the lab director, division director at that time, who really fostered this work and said that this was important to do, even if it wasn't obvious at the time that it was right down the main line of the mission of the division and lab. But he was able to recognize the fact that one of the real jobs of a laboratory like this and of a division like this is to catch the possibility that something may turn into something important and be able to foster it and help it grow, even when there's all of the obvious criticisms of any new idea at the time. And that, I think that's a real credit to understanding what it means to be a director of a division and understanding what it means to be a scientist and to make this kind of thing work. And the fact that you could do that at a place like this, Berkeley and Berkeley Lab, is also something that's, you can't find very many places. I think, as Chancellor Birgeneau had said, this is an unusual place for allowing both these groups of people to exist, and also the support that you can get at a national lab. And the fact that the DOE had that sense of responsibility towards pushing forward the fundamentals of science in that way, it meant that you could actually work for a project that, I at the time advertised it was going to be a very hard project when we first proposed it, that was going to take us at least 3 years. And of course, 10 years later, we actually started having results, but I don't think any of us regretted it, and I don't think that in the end, DOE or the labs regretted it at all. And it's because of that long-term vision, that capability of providing support over more than just one little funding cycle, that we actually have national labs, and that we have this kind of environment where you get to propose something that's a little bit bigger and work on something just a little bit longer. So those were the, I think all the elements that you needed to make it possible to do this kind of work. So finally, of course, in the end, it all boils down to the personal, and the fact that this team of scientists that those of us left in the room represent. And actually, I should mention the one who's not here today, Gerson Goldhaber, who died recently, and we're sorry that he isn't here today to enjoy this with us. But all of us, I think, as scientists, depended so much on that support and the involvement of our families, and the fact that they were there, willing to put up with us disappearing for nights and nights on end, or days and days on end, as we worked round the clock to generate these groups of supernovae. And we'd be there at the end of the phone call. My parents, who are still probably the people who will get the most out of this Nobel Prize. And I think that sense of how, as a community, we were able to do these things together was really come out of the fact that we were supported by such strong families and communities around us. So, of course, with that, I have to thank my daughter and my wife for putting up with me ever since. And I hope, and thank you.
Okay, ready? Yes, okay, start. So we'll begin the media questions at this point. So if you have a question, please raise your hand. We have some handheld mics. If you could identify yourselves and the outlet that you represent. So any questions? Anyone here? Right here, Mr. Perlman. You should go first.
Hi, well, congratulations. I'm Dave Perlman from the Chronicle in San Francisco. You've been awfully helpful to a lot of reporters over the years, explaining what this is all about. But one thing that I haven't asked you, or I don't know whether anybody else has, is there any relation that you see between what is known as, what you know as dark energy, and what a lot of people talk about as dark matter? If there's dark energy pushing the universe farther apart, what role does dark energy play?
So for those who may not sort of recognize the problem, that there are these two vast unknowns that we have now identified in cosmology. One is about 20% of the universe is what we call dark matter. So this is what we think could be relatively conventional stuff by comparison, which just doesn't glow in the dark. And we think it perhaps could be new particles that we haven't yet identified. We know that it exists because it holds galaxies together, rotating faster than you would have thought if that matter weren't there. And so that's a big part of a big problem that we've known about now since the late 60s, early 70s. So 20% of the universe is there. We believe that on the order of 73, 75% of the universe is in this other form of dark energy that's responsible. In fact, the only reason that we're calling it dark energy is because it's what we think of as causing the universe to expand faster and faster. And at the current state of understanding, we have no good tie between them. So if you ask the theorists, they'll say, well, they seem to have very different properties. We don't recognize them as coming from the same part of the story at all. But there's certainly a sense that what we're looking for is some theoretical concept that will solve a few problems at the same time. So one possibility, and some theorists have been pursuing it, is could you possibly come up with a slight modification of some part of physics that we know of that will suddenly get rid of the need for dark energy and dark matter in the story, and that will make everybody happy, and then you'll know you're on the right path. I would say that 99% of the theorists think that's very unlikely, but it would sure be it would be very convincing if you suddenly got that all to work all at one time. And I'd say that since we don't know the answer to either of them right now, you can't dismiss it completely.
Any other questions? Yes, one up here.
Yes, my name is Pilar Niño. I am a reporter with Telemundo. I'm curious to know if you ever dream of winning a prize like this, and also if you can remember times in your life where you feel kind of losing confidence and that maybe you are not going to accomplish anything. I don't know, a person like you will have those kind of doubts, but I guess a lot of people are looking for goals in their lives and maybe they never dream with something like that, so what would you tell them?
No, I mean, it's a very good question because at the time when I was a graduate student looking around for a project to work on, and I was here at Berkeley, actually. I'm one of the few people who end up sort of getting stuck. It's a great place to be stuck. And at the time as a graduate student, I remember talking to my friends and saying that, I want a really meaty project to work on, and I want it to be something where I felt like I could actually make a difference and be involved in helping develop it and design it. But I didn't see anything immediately out there that I knew I wanted to work on. And I tried one research group for a little while. I moved to a different research group, and I kept talking to my friends about, I wonder, what could I possibly work on that would feel like it was satisfying and worked well. And when it comes down to it, I imagine that there's just a huge amount of luck involved, that I was looking for something fundamental. I thought that perhaps you could use astrophysics as a route to doing it. These tools became available just around the right time to make it seem possible to approach this problem, and I was able to start working on it. Now, I think the part that goes beyond luck is that you then had to put up with the fact that people were not saying, oh, great, come and do it and we'll give you money. The first reaction is that will never work, and here are all the reasons why. And you had to keep trying to explain, no, I really think that this is doable, and if you put the same kind of effort into this that we see going into many other projects, we should be able to accomplish this. There's no reason that we shouldn't be able to answer this question if it's available to us. And so I think it's probably good for people to realize that sometimes it just takes patience looking around for what you think is the project and the work that you should be doing. And then after that, sometimes it takes a lot of stubbornness to be willing to get people to be willing to let you do it.
Other questions? Yes?
Dr. Wayne Friedman with ABC7 in San Francisco. 3 questions. The first one is just a simple yes or no. Did you get a perfect score on your SAT?
I got to remember, no, it wasn't perfect.
Well, then there's hope for a lot of people, including my daughter. The second question is really a 2-part question, and that is, given that we don't know, or you don't know, and you haven't found 80% of the universe, is that humbling to you personally? And as just kind of a being in this universe. And the second part of it is, how do we relate this? How does the average person at home, when they hear about dark matter and not knowing what it is, how do we explain the relevance of that to them, potentially?
Yeah, no, okay, well, so there are a number of different answers to different parts of the question. I mean, first, when you consider almost any aspect of the universe, even the very local universe, you can't help but feel humbled, right? I mean, even just the scale of the Earth with respect to the nearest sun, or our galaxy, and then our galaxy among all the other galaxies, and then you consider the possibility that the universe is infinite. I mean, as soon as you consider any of these things, your mind is boggled, and I think you have to enjoy having your mind boggled to go into this kind of field. I think that's part of the pleasure, and then you end up developing a bit more of a hubris about the whole thing, because the fact that we're, as human beings, that we're able to talk about all this stuff is, I think, remarkable. I mean, why have we evolved on this Earth where there's no reason that we have to be able to deal with the much larger universe around us? Why is it that we're able to even ask these kinds of questions? And then you start getting kind of cocky, and proud. And then you finally realize that all you've managed to figure out is that we don't understand most of the universe. And so I think it brings you back to ground and puts you in a nice, comfortable place right in the middle of feeling, well, we didn't do so badly, but we're not doing great. And I think that's a nice place to sit in. And it's nice to be living in a universe where we somehow manage to magically be sort of in a middle scale, where we get to look way out at these vast distances and microscopically way down at the tiniest particles, and that both are relevant to our understanding of where we fit into the world. And the amazing thing is that the more we learn about these apparently irrelevant parts of the world, these fundamental physics parts of the world, the more we seem to be able to do in this part of the world that we live in. I mean, there's no reason that should have been the case. And yet, somehow we're flying airplanes, and we went to the moon, and I mean, you wouldn't have thought that would be relevant. And yet somehow, when you learn things about the world, and when you're driven to learn things about the very most fundamental things in the world, you end up inventing things that I don't think you otherwise ever would have invented. And I think that's maybe the way to describe its immediate relevance to us as humans, aside from this amazing poetic relevance.
And the next question? Here.
How do you explain your work to your daughter?
Well, you have to ask her, but but I think that one of the things I actually also love about this particular project and this topic is that the elements of the story are actually fairly easy to describe. I mean, you can discuss how you can measure how distant something is by how faint it looks. Does that make sense? Yeah. I'd say the redshift is a little bit more complicated, but I described the universe expanding, and I think Noah's been telling her classmates about that. and it's one of the few times I find that you can be sitting in an airplane, next to a random person, and they'll start asking you about what you're working on, and you'll just say a few words, and they understand it at a deep enough level that they start bringing up exactly the objections and the concerns that you have about the work. And I thought, now that's remarkable, that that people just hearing it for the first time get it at a level that's direct enough that they can start suggesting what things could be wrong with the measurement that we need to check, which is what you love to hear.
Okay, other questions? Here.
My name is Jia Jun. I want to know that if we find a new kind of particles, and how do we classify it as dark energy or dark matter? I mean, what's the difference between dark energy and dark matter?
There's one property of dark energy which is completely different from anything else that we've come across, and that's that it actually acts as a how do you describe it? As a negative pressure, which is you see it in the equations as a negative term, but it's very hard to describe. It's almost as if it makes space sort of bouncy, a little elastic. And almost any other particle that we come across doesn't have that elastic, bouncy property. It tends to attract, it tends to make the space curve around it. This has this opposite effect on the universe. And I now have to take back what I just said a second ago about understandability, because this is the one part that I have never been able to find a good way to capture and explain it to other physicists, let alone to my daughter. And I've even occasionally pushed people who, like I felt, okay, I'm just a lowly experimentalist, who measures things. So I've gone to people like Alan Guth, who had developed the inflationary theory, because they have the exact same problem, that during the period of rapid inflation in the early universe, there's this repulsive quality to these fields that they're describing. And I asked him, could you give me a little bit more of a way of describing it to other people? And he ended up throwing up his hands too. He said, well, it's in the equations.
I'm a reporter from China's Xinhua News Agency. So there is some concern, I think, also in this country about the weakening of the interest for the young people in science and I think particularly basic science. So I think what's your maybe suggestion for young people that who are looking to pursue a career of science, like your, maybe for instance, if your daughter, yeah. So what your advice for?
I mean, my personal experience is in giving talks and talking to students in other settings, that there seems to be no weakening of interest by the students themselves. I mean, I think they're all on board and they're excited. They would love to do more. And I think that it's one of these moments where it's hard for all our societies sometimes to recognize that this is one of the places where where an investment is really paid off multifold. I mean, that by investing in these kinds of activities and exciting the next generation of children, they get motivated to learn all sorts of things. And they may not become scientists, but the things that they will have learned by going through the process of thinking about science are the things that help us move forward as a society and solve all sorts of problems. And so my hope is that the whole point of these kinds of prizes is that it gives a moment in which people step back and have a moment of reminder that this is part of what it means to be a human being, and it's part of what made us so special, and made it possible for us to build these amazing societies and civilizations that we've built.
Next question. Right here.
I have one. I think, do you get a nice parking space now?
I was saying that probably the single most important thing about Nobel Prize for most people is if you can get the parking space, the coveted parking space on campus. And so, so I'll find out. But I'm looking forward to seeing if you could drive someplace.
No.
Now it's all been worthwhile.
Do you have a parking place here?
I think so.
Yes, you do.
Oh, you do? Okay.
Yeah. Any other questions?
Yeah.
Yes, Dave again.
When do you go back to work?
I'm assuming that after lunch, we'll have a few minutes to remember, okay, now which paper did we not finish? And then, where is that referee comment?
Yeah, it's one right here.
Doctor, based on the pinnacle of where you are now, what are some questions you have? What are some things that you would like answers to at this point in your life? What's the next threshold?
Well, I mean, obviously, this particular discovery, has triggered so many questions that we'd love to get make progress on, and we've been inventing and building and designing things and all sorts of people in this room and around the world have projects that they're ready to go with, and so we're hoping that this kind of result will encourage the chance for us for those things to move forward, and that the resources become available to do that. But of course, there's so many questions in the world that you'd love to work on, and it's always just a question of looking around and trying to decide which ones can you take the time to do next.
Thank you again for coming. Congratulations to Saul Perlmutter. Great.